Hello my dear friends, welcome to my YouTube channel. Today we will talk about how to write a code in Silvaco TCAD tool. If you are beginner and don't know anything about the Silvaco TCAD tool, please listen this video very carefully. After that you can understand how to write a code in Silvaco TCAD tool. Let's start. For write a code in Silvaco, you have to write first Go Atlas, running Atlas inside deck build. Second method, you can run a Atlas with a given version. For example, Go Atlas simflags equal to the version v5.10.0.r. And the third step is running Atlas without deck build. To run Atlas directly under Unix using the following command. I will not prefer to follow this step. Let's go to the code. First open the deck build. In this presentation, I will explain you how to write a double gate MOSFET TCAD code in Silvaco. First, I have written the command Go Atlas. Different statements in Atlas input file. If you are writing a code in the Silvaco, you have to first define the structure specification, then material model specification, then numerical method selection, solution specification, and result analysis. In the structure specification, you have to first mention the mesh region electrode doping. In the material model contact interface, and the third one method you have to define, then log, then save, and the Tony plot. I will explain you how to write a syntax in Silvaco TCAD tool. Any input line in deck build is referred to as a statement, just as Go Atlas. Go Atlas is a statement. Since statement and parameters are not case sensitive, it is not the case sensitive. You can write it into upper case letter or lower case letter. They can be entered using either uppercase or lowercase letter. A statement is specified in the general format. Statement parameter equal to value. Statement, for example, reason. Parameter means you have to assign the rectangular area with the help of the positional parameter x minimum, x maximum, y minimum, and y maximum. Next, you have to define the value. The space character is used to separate the parameter in a statement. Using command language to define the structure. Specifying the initial mesh, you have to first write the mesh space dot multi equal to value. This is followed by a series of the x mesh and y mesh statement. X mesh location value spacing value, y mesh location value spacing value. Let's go to the code. I have started with the command mesh space dot multi is equal to 1. I will explain you what does mean. Using the command language to define a structure. To define a device through the Atlas command language, you must first define a mesh. The mesh or grid covers the physical simulation domain. Specify the initial mesh. The first statement must be mesh space dot multi is equal to value. You can assign the value 1, less than 1, or greater than 1. It is actually a multiplying factor with the meshing value. If you are choosing the 1, then the spacing value is same. If you are using the multiplying factor 0.5, then it will make the meshing coarse. For example, the spacing is 10 nanometer. Then it will be multiplied by 1 by 2 and it will become 5. If you are decreasing this mesh space dot multi value to less than 1 continuous, it will make the meshing will become more coarse. If you are increasing the value of this mesh space dot multi to greater than 1, then it will find the meshing. In most of the cases, we have taken the value of mesh space dot multi is equal to 1. In my example, I have taken the value is equal to 1. After that, I have defined the x meshing, then y meshing. X meshing location, you can write complete location or you can write LOC. X dot mesh, you can also write in uppercase letter or lowercase letter. Then the x mesh location is 0, starting from the 0 and end at the 250. Actually, the value is in micrometer. If you are convert into nanometer, then multiplying by the 1000. Then it starts from the 0 to to 250 nanometer with different spacing. From 0 to 5 nanometer, the spacing is 0.001, 5 to 10, 0.001, 10 to 15, 0.0005, 15 to 20 is again 5 nanometer, 20 to 25, 10 nanometer, and at 25 it will be 1 nanometer. It will automatically change the meshing style. For example, if you are moving from the 0 to 5 nanometer, the spacing is 1 nanometer, 5 to 10 nanometer, the spacing is 1 nanometer, and at point 10, the spacing is 0.5 nanometer. When you reach at the point of the location 10, it will automatically change the meshing to about 0.5 nanometer. After that, I have defined the Y dot meshing with the same method. Once the mesh is specified, every part of it must be assigned a material type. This is done with the region statement. After defining the mesh, you have to define the material type in every region. Please note down that every region of the meshing must be defined any material type. If any of the region will not mentioned by any material type, then you will get the error in the code during simulation. After defining the meshing, I have to define the region statement. Region number statement must be start from the 1. Region number must be integer type. After that, you have to define the material, and after that you have to define the positional parameter. Region number start from the 1 and increase for each subsequent region statement. You can assign up to 15,000 region in ATLAS TCAD code. First I have defined the region number, then the material type is air with the positional parameter x minimum, x maximum, y minimum, y maximum. If you don't mention the x maximum, then it will take automatically the maximum value. The maximum value in this case is 250 nanometer. Then air must be inserted into from 0 to 250 nanometer in x direction, and in the y direction from 0 to 20 nanometer. Region number 2, material is SiO2. Region number 3, material is SiO2 with different positional parameter. Region number 4, 5 and 6 having silicon material type with their different positional parameter x minimum, x maximum, y minimum and y maximum. Next is electrode. Once you have specified the regions and materials, define at least one electrode that contact a semiconductor material. This is done with the electrode statement. You can specify up to the 50 electrode. For example, electrode name. Next you have to define the electrode name, gate, drain and source. And next is the positional parameter x minimum, x maximum, y minimum and y maximum. Example given below: electrode name gate, x minimum, x maximum, y minimum and y maximum. If no y coordinate parameter are specified, the electrode is assumed to be located on the top of the structure. You can also use the right, left, top and bottom parameter to define the location. One other method to define the electrode without positional parameter, you can define with the help of right, left, top and bottom commands. For example, electrode name source, we have to define the source metal in the left side with the length of 0.5 nanometer. In this example, I have defined the 4 electrode statement. We are using the double gate, so I have taken 2 gate terminal, gate and gate 2 with different positional parameter. Electrode name source with their positional parameter, electrode name drain with the positional parameter. It's very simple to define. After defining the electrode statement, you have to define the doping. We specify the doping using the doping statement. Doping distribution type, either it will be uniform or non-uniform. Dopant type, N-type or P-type with the positional parameter x minimum, x maximum, y minimum and y maximum. Analytical doping profile can have uniform or Gaussian form. The parameter defined the analytical distribution are specified in the doping statement. I have taken 2 examples, one for the uniform doping and one for the Gaussian doping. Doping uniform concentration 1E16, dopant type N-type, and the positional parameter, you can also define the region number. I have chosen region number 1. Next, I have defined the doping Gaussian type with the concentration 1E18, characteristics 0.05, p type, x left 0.0, x right 1.0, and the peak value is 0.1. The first doping statement specify a uniform n-type doping density of 10 raised to power 16 per centimeter cube in the region that was previously labeled as region 1. The positional parameter x minimum, x maximum, y minimum, y maximum can be used instead of a region number. Doping uniform 1E18 in the channel region, or we can take 1E16 and 17, p-type concentration. Doping uniform concentration, source side 1E20 and the drain side is 1E20. Dopant type, n-type, n-type, and the position parameter are defined by the region number, region 4 and 6. Next, specifying material properties. Semiconductor, insulator or conductor. All materials are split into 3 classes: semiconductor, insulators and conductor. Each class requires a different set of parameters to be specified. For semiconductor, these properties include electron affinity, band gap, density of state, and saturation velocity. When defining new material, there is a minimum set of parameters that should be defined. This set includes band gap, electron and hole density of state, dielectric permittivity, and electron and hole mobility. It is denoted by a different syntax. Band gap Eg 300, density of state Nc, Nv 300, permittivity you can define with the permittivity, and the mobility of electron and hole MUN and MUP. I have defined the one material which is already in the Silvaco, that is silicon. I have defined the electron band gap and the mobility of electron. Band gap 1.12 and the mobility of electron 1100. Specifying material property continued. Setting parameters. The material statement allows you to specify your own value for these basic parameters. Your value can apply to a specified material or a specified region. For example, the statement material silicon, electron band gap 1.12 and the mobility of electron 1100. If the material properties are defined by region, the region is specified using the region or name parameter in the material statement. For example, the statement material region 2 with the property of TAUN 0 2E-7, TAUP 0 1E-5. If the name base has been defined using the name parameter in the region statement, then the statement would be material name base NC 303E16. You can define the material 3 types. First, you can define the material and change their property. Second, you can define the region and apply some property to the region also. And you can use any name at the base, for example, with the different properties. Next, you have to define the model statement. Models specify model flags to indicate the inclusion of various physical mechanism, models, and other parameters such as global temperature for the simulation. Different syntax is used for the model statement. First one is CONMOB specifies that a concentration dependent mobility model be used for silicon and gallium arsenide. CONSRH specify Shockley-Reed-Hall recombination using concentration dependent lifetime. SRH specify Shockley-Reed-Hall recombination using fixed lifetimes. AUGER specify Auger recombination. BGN specify band gap narrowing. FLDMOB specify a lateral electric field dependent model. Print prints the status of all models, a variety of coefficient and constant. For detailed study of these models, you can go for the Atlas manual. Models I am using the same I have explained in the slide: concentration mobility, SRH, Auger, BGN, field mobility, and print. Simple print command is used to copy all the MOS parameter in the model statement. If you don't know which model you are using, which model you can use for this particular structure, you can write simply model MOS print command. Print command will automatically copy all the models related to the specific structure. After defining the model statement, you have to define the contact, work function for gates or Schottky contact. An electrode in contact with the semiconductor material is assumed to be default to be ohmic if a work function is defined. Then the electrode is treated as a Schottky contact. If the work function is not defined, then it will be treated as a ohmic contact. If the work function is defined, it can be treated as a Schottky contact. The contact statement is used to specify the metal work function of one or more electrode. The name parameter is used to identify which electrode will have its property modified. The work function parameter set the work function of the electrode. Contact name, gate, work function 4.8. The work function of the several commonly used contact material can be specified by using the name of the material. Simply, you can define the work function in two ways. You can directly write the work function. For example, I have written 4.8 at the gate terminal, or you can use the material name also. For example, aluminum and polysilicon. You can use any material which has been already mentioned in the Silvaco TCAD tool. In the contact name, I have defined the gate 2, source and drain. I am applying the work function at the gate terminal. I am not using any material name. I am simply defined with the work function command. Gate work function 4.8, gate 2 work function 4.8. This means we are using the same gate material for double gate structure. If you want to apply the same voltage at the gate terminal, then you have to use the command common is equal to gate. After applying this command, if you are applying the voltage at the gate terminal, you will get the same voltage at gate and gate 2 terminal. Next command is interface charges. In my last video, I have already explained about the interface charges. I will take a brief note on that in this video. The interface statement is used to define the interface charge density and the surface recombination velocity at interface between semiconductor and insulator. You can define the interface with two types. You can define at a particular region, or you can use it as at every region of SiO2 interface. Interface QF3E10. This statement specifies that all interface between semiconductor and insulator have a fixed charge density of 3E10 per centimeter square. Or if you have to define for a particular region, you have to define the positional parameter. For example, interface with their positional parameter x minimum, x maximum, y minimum and y maximum. The charge density is 1E10 with S.N 1E4, S.P 1E4. It will represent the surface recombination velocity at SiO2 interface. After interface statement, you have to mention this command: output, valence band, conduction band, QFN, QFP, electric field, mobility, electron and hole, electric field in x direction, y direction, electron hole mobility, temperature, potential in electric field. If you mention this code in your Silvaco TCAD code, then you can find out the various parameters from the structure file. If you did not mention this syntax, then you will not find out the potential energy band diagram from the structure file. Please note down this command very carefully. After that, I have defined the method statement. Method statement I also defined in the previous video. I will take a only brief note in this video. In method statement, there are the various numerical methods to calculate solution to semiconductor device problem. There are three methods: Newton method, Gumail method and the block method. The Newton method solves all unknowns simultaneously. The Gumail method solves for each unknown by keeping all other unknown constant. This process is repeated until there is a stable solution. And the block statement is a mixture of Newton and the Gumail. It will solve some equation with the Gumail method and some equation with the Newton method. The block method are mainly used when the lattice heating and energy balance equation are included in the structure. You can also define all the three numerical method in the simulator code. First, it will choose to solve the equation using Gumail method. After that, block method. If no solution method are specified, then Newton is applied by default. If you did not mention any method statement, then it will automatically pick Newton method. Then solve statement is used to find out the one or more fixed solution. Solve initial, solve previous, solve V drain voltage from 0 to 1 volt. You have to mention this voltage increasing gradually from 0 to 1 volt. If you direct specified V drain 0 and V drain 1, then convergence problem take place. After applying the drain voltage, you have to apply the gate to source voltage. First, you have to apply the command log outf. You have to create the log file. Next, you have to apply the gate to source voltage. If you want to find out the conductance and the capacitance, you have to mention solve AC frequency 1E6, name gate voltage is increased from 0 to 1 with the step size of 0.05. And in the last, you have to save the structure file, and with the help of the tonyplot command, you can observe the structure file and the log file. And the last, quit command. When you run this code, you will get the two files. One is structure file and one is log file. Tonyplot will help to observe these two files. When you run this program, you will get the both file in the Tonyplot window. I will show you. This one is the structure file and this one is the log file. If you want to see the result in log format, click on log. OK. The value of the off current lies between -1 and -12, and the on current is greater than -4. It is actually in between the -3 and -4. With the help of the optimized meshing, you can improve the result. You can decrease the off current up to the 15 or 16, 10 to the power -15 or 10 to the power -16. If you want to extract the result from the log file, first you have to do select it, file, save as. You have to select CSV format. You can give the name, any name, for example Girish, my computer, D drive, save. A file already exists with the name. Do you want to overwrite it? Yes. Your data has been extracted. In the next video, I will explain you how to extract data from the structure file. This is end for today. Thanks for watching.